Thank you, everybody, for joining our session. Today is only me. My friend Kali cannot join. So about myself, so you pronounce my name as Haohai. Yeah, it's easier for you. So I'm the software architect in IBM Spectrum Computing team. I'm not that software architect who likes talking, playing around the PPTs. I'm still coding a lot. So all the jobs we are going to talk today are my babies. So hopefully I can deliver them as much simple, straightforward as I can. So we are based on IBM Canada in Toronto. So IBM's Spectrum Computing provides our homegrown Spark edition that serve like a Spark, IBM Spark as a service in the IBM Cloud, and also a bunch of customers. So today we are going to review a journey we went through in the past 2 years. The journey starting from running Spark workload in containers to put the entire Spark cluster onto a multi-tenant Kubernetes environment. So we're starting from what's the benefit you can get from running container, and also what's the solution, how to migrate Spark non-container-based Spark workload to be container-based one. So the second stage is we move the entire Spark cluster into Kubernetes. So I try to abstract the structure and the workflow here, and how to achieve multi-tenants on top of that. At last, some future works we want to pursue at the next stage. So why use containers? So first of all, for your Spark workload, especially in a multi-tenancy environment, it's not uncommon to see one user submit like a batch job. That batch job can eat up all the CPU cycle in the node, and or consume all the memories. That squeeze no space for other users' job. So if you have, like us, we provide a fine-grained scheduling backend, so that can assign tasks dynamically to the executor. So basically, we want to achieve, for example, you have one executor, you run 5 tasks at that moment. So you want to control the CPU share is 500% of your total physical CPU time. But if you have the reclaim or preemption happen that the executor tend to only run 3 tasks, then you should load down to 300%. Also, Spark has built-in parameter like define how much memory you can use for the executor JVM. But that parameter just turns to a maximum setting for the JVM, which cannot control the entire process group created from that JVM. Because the JVM, the user logic in the JVM could use off-heap memory, could spawn other sub-processes that can take more memory than you defined. And the Spark or your backend system cannot control that, cannot enforce that. Secondly is it's not if you look at the product cluster, it's not easy to just, whenever a new version of Spark published, you just move to that version. So in the production, you always see they support multiple Spark versions. They concurrently running in the same cluster. let alone user applications. They depend on certain versions of Spark. So it turns to very hard for the cluster admin to maintain those deployment dependencies on the same host file system. Of course, from the DevOps point of view, they want to create once and deploy everywhere. So in the case they want to create their application level image. So to launch a container, you need an image, right? But we can end up two situations. One is okay, I have my application logic, I build my image. So I want to run somewhere in the Spark cluster. So in the case, we don't want user take the Spark version into account. For example, I built an image. I have to build in a appropriate Spark version inside. Or I need to run like a testing floor. Do I need to build a testing floor, the entire testing floor into my image? That turns your image to tens gigabytes. Secondly, is if you have an existing Spark cluster that's running non-container-based workload. So can we seamlessly migrate those workloads into container-based? So to keep so both situations actually end up one important thing for us, we always keep in mind when we design the whole solution is why we need people take care of the Spark version, why they need to build an image for them. So let's examine a regular Spark workload. So it's easy, simple. So Spark submission goes to Spark master. Spark master find a place to run your Spark driver and then Spark executors. So those processes launched by JVM, as long as they can find like the Java running, some fundamental thing like the Java running time information and the Spark installation and even some like Python, some dependencies, then they are good to go. So they launch as the JVM to run. So if we move this particular Spark workload, Spark job into container-based environment, it turns to like this way. So why it can be this? Because if your backend system can take care of all the dependencies and automatically mount when you launch the container. So in this case, I don't need the image because I have everything already in my host file system. So I can pick up whatever base OS image and just put the JVM inside the container. Then I can run, right? So here we can solve the first issue is the resource enforcement. Of course, if you have your own application logic, so you want to build your own image. But when you build the image, it don't require you take care of the Spark distribution, all the dependencies. So you just need to fill up this form. This form need you give we call it a container definition. So you need to give a name. And then the image name you build, you want to deliver to the cluster. And also where you need the cluster to retrieve that image. If you have extra dependency from the host that the backend system doesn't know, you can define data volume. So basically, see where you want the system to find your dependency and where you want to mount into your container. So after that, you can use like this command. It's an example for the Spark submission in cluster mode. So you can define your driver to run as use the definition I just defined, right? And the executor as well. So after that, the workload run as this way. So you see the container is launched by your image. I just defined the image, my app image version 1. And this container will automatically mount all the dependencies that the Spark running things, like the Spark installation from host file system, as well as the things you defined, like this, I make up the name info-bench.lab, right? So then your workload is good to go. Actually, this is the solution we migrate existing Spark workload into a container-based one. So from this diagram, actually, it's not really solve the file system level dependency conflicts, not really solve. So it's just solve okay, you can put your application level dependency into your image, but you still relies on the host file system most of the time. So the next stage is we think about, can we move the entire Spark instance into Kubernetes? So, of course, let's start from the bonus. In addition to the running in container, if you're running in Kubernetes, what else you can get? So first of all, you can increase the resource utilization because your Spark cluster is not only one resident in the Kubernetes cluster. You have a surrounding ecosystem, right? So in this way, we can further isolate, like we mentioned, the host level dependency conflicts. We go further, actually, we isolate, depends on the tenants. And of course, the tenant level, because if you go to you subscribe public cloud, you define like you are an enterprise user or a pay-as-you-go user. So based on your subscription, the cloud provider should give you a quota against that, right? So if you are a pay-as-you-go user, probably you only can run 10 containers. So in this way, if we can isolate based on the tenant, then we can easily map in your tenant price plan into it's a resource quota. Of course, Kubernetes can help you to roll out your update to simplify the deployment overhead. So I try to abstract the structure as this way. It's a two-layer abstract. So let's look at the bottom up. So the bottom level, it's called the tenant level. The top level is we call it the Spark as service level. So the bottom level, we introduce a concept is called a Spark instance group. So Spark instance group is a Spark notion of a tenant. So we can look at from the different perspective. So the diagram shows you, if you look at from the Spark service or Spark components perspective, one Spark instance group consists of they have their own Spark master, history server, even shuffle service, and a certain edition of notebook. So if you look at from a deployment perspective, a Spark instance group can have a certain appropriate Spark version, plus the configuration to tune up this Spark, and also Jupyter or Zeppelin notebook version, plus the user application you want to put into this instance group. So from the Kubernetes perspective, a Spark instance group is a first-class deployment. The nice thing here is that after you define the scope of your Spark instance group, we automatically generate an image for you. So this deployment in the Kubernetes is initially only one container. That container will contains all the components and services inside. So after that, the admin can manually adjust the replica of the of the deployment based on the tenant's price plan. Furthermore, we can, as long as you have the enough resource quota, we allow this Spark instance group automatically scale up and scale down based on the current Spark workload demands. So this is called the Spark instance group. Then the top layer, it's our product name. It's called IBM Spectrum Conductor with Spark. So this one is actually it's one container. We call it a master container, but actually it's just provide some endpoints. So one endpoint for admin from the user perspective, some endpoints for admin to control, to manage the lifecycle of Spark instance group. From the user perspective, they use the endpoint to manage their Spark workload and get first-hand the Spark information. So I just gave the Spectrum Conductor with Spark a short name. It's called CWS. So CWS is we predefine as a Helm chart. So you can use a Helm install to install it. And it's only run as one container. So if you put this infrastructure into the use case, we can treat if you put it into the public cloud, so one CWS, it can provide one Spark as service. And if you put it into the on-prem cluster, then you could define one CWS for one business unit. So this is the command to create one. This is the case to create one CWS. It's a Helm install. I give this is the name. In Kubernetes Helm install, this the name is the release name. But we use this name as the prefix name for the entire domain, including the SIGs underneath and the CWS master. And also we create a namespace, specific namespace for this domain. So the namespace we can create actually at the two layer. One layer is in the entire domain CWS layer. Or it could be in the tenant layer. So after you submit that command to Kubernetes, then it turns to you will get a new namespace. It calls like I created NIS4BU1, and I got one container is called the CWS master container. So this container will expose a web GUI interface. So you got CWS is called the SPAS for BU1. Because it's exposed the web URL, so you can as the service, so you can access from the outside world. Then go to the web GUI. There is an interface to create a Spark instance group. Here I just give a very simple example. Is you need to define like a group name, which Spark version you want to put into, and plus the configuration you want to tune up, and also the notebook version. Also, you can define like or upload or attach your own libraries. So after that, this creation will generate an image for this Spark instance group. That image will put into the registry you specified. So after the flow, you got because I define this instance group name as the tenant one, you got a tenant one image in the registry. So after that, Kubernetes will create first the container based on the image we just generated and get a deployment. So the bottom diagram is a Spark, is a Kubernetes dashboard. So from here, it shows two, every row is a deployment, and some metrics like namespace, what's the namespace, and what's the desired or expected number of container, and available is the real number of available container assigned to the development deployment. So The good thing is the story is not end just a deployment. So the user, after this instance group created, user can log into the CWS endpoint and open the web GUI to submit their workload or start their notebook. So that will trigger real Spark workload come into the instance group. So that workload probably need more container to run in order to get a better performance as long as you have the enough quota assigned to you. So this is the case. So how we do this? It's a little bit tricky is that because every SIG Spark instance group, they have one Spark master. So this Spark master will collect all the workload in that instance group and aggregate and made a decision to talk to the Kubernetes master, see how many pods I need to create for my entire group. So then the group, all the executor in this group, they can run in the new container. The better thing is that if one workload, one job finished, that executor will be, the executor is done. So in the normal case is you need to return that pod back to Kubernetes. But in the case, the pod will return to the Spark master. So Spark master will make a next decision based on if there is other demanding in the group that requires to run another executor. So we give the more chance possibility to share pod across within the Spark instance group. So this is the case you see the bottom chart is now my Spark master requires 6 pod, and the Kubernetes give it 4 at this moment. So this, I did experimental performance comparison between without dynamic scaling, we just did, and with dynamic scaling. So this chart is the left top one is the number of running tasks at any moment. The right part is the finished task ratio. So you see because my running task always 3, so the finish ratio is a linear one. So this with the dynamic scaling, because I have more pods joining my group, so I can run more executor. That executor can serve more. In my case, one executor can run 4 tasks. Then you can see I have more tasks running over time, and the finish ratio is a steeper. It's a big slope there. So in terms of time, one is the 15 minutes in the same job. The other one is just half time. So how to achieve multi-tenants? Actually, we can achieve 2 levels of multi-tenants. One is in the same instance group, I can define multiple tenants. Each tenant is a whole, they are totally isolated Spark instance. So for each tenant, I have their own image here. We can go further we define multiple Spark as service. So this is the command, just like the previous one. I define 2. One is a SPS for PU1, another is PU2, and each one has their own name and their own namespace. So we try to fully isolate them. Then it turns to the diagram like this. So you can see I have 2 namespace for the 2 domain, 2 Spark CWS, and each one has their own Spark instance group. Okay, so I try to conclude with this comparison, a survey we did. So the first column is some metrics we pick up to compare different Spark on Kubernetes approaches. So the second column is the one now in the open source will be published in next version of Spark. The third one is a lot of people did some pioneer job to put the Spark on Kubernetes. The simplest one you can get from the Kubernetes example catalog. Those we all put them into one column. The last one is us. So it's just for reference. You can see we compare like if they support a dynamic allocation based on the workload demands, what granularity they interact with Kubernetes master, and do they provide deployment automation, etc. So some future works. First of all, the current Spark. So you see our architecture, actually we need 2 layers of resource management editing. So now we only, in the Kubernetes, adopt only one. We either define a namespace level, tenant at the namespace level, or the entire CWS at the namespace level. So we want some further fine-grained resource management ability in Kubernetes. Fortunately, there is a Kubernetes arbitrator. It's on track, so we may integrate with them later. The second one is we will continue the topic by doing some more serious performance benchmarking against like our solution and the other even open source solutions. Okay. I think we leave 3 minutes for any questions, comments, advance. Yeah. Thank you.
Hi. I was curious on how you manage the data in this Spark instance groups. Like, how does get data loaded? Because since it's dynamically allocated, how do you ensure data locality and stuff?
That's a good question. So I did not show in the one chart. We have we call data connector. So basically, that data connector abstract all the data accessing interface. For example, you can use that one to access like HDFS, or it's a part of the definition in the SIG. So make sure that any application in that SIG can access those data stores. In terms of data locality, that's true. We currently we don't put the data locality support as the higher level priority job. The reason is that if you look at the current the data lake or data store solution, data locality is not that important as the time back to the MapReduce state, right? So, but we definitely will support in the if you have a smaller scope of HDFS cluster, we still need to take that into account. Right?
Thank you.
Thank you.
If there are no more questions, let's thank Haohai for his talk. And the next talk will be at 15:20.